First thing I want to talk about today, so this is just 12.5 part 2. More curvature. In the plane, so we came up with a formula for curvature for a vector valued function. Well, we can simplify things a little bit if we have a curve in the plane. So we have a curve given by y equals f of x. So just our normal explicit function. Let x be the parameter. So we can say r of x, our vector valued function, if we write it this way, xi hat plus f of x j hat. It's my x and my y. So r prime then is just I hat plus f prime j hat. And the magnitude of r prime is the square root of 1 plus f prime squared. Does that look familiar? That's what we integrate to find the arc length for a function y equals f of x. Not a coincidence. Our double prime, I'll write that here. Our double prime is just f double prime j hat. And r prime cross r double prime is equal to, we'll do this determinant, I, j, and k, 1, f prime, 0, and 0, 0, f double prime. Sorry, 0, f double prime, 0. And this just comes out to be f double prime k hat. And the magnitude of r prime cross r double prime that we need for our curvature is just the absolute value of f double prime. And we can say that our curvature k is the absolute value of f double prime over 1 plus f prime squared to the 3 halves. And that would be our formula for curvature for a function in the plane y equals f of x. Well, since this is we just get a number out, so that's going to be absolute value. So this is a scalar function.
Because there's 2 bars.
Oh, this I wrote 2 bars here. Thank you. All right, so this gives us a way to find the curvature in the plane a little more compactly than our other method. All right, questions there? Okay, the next thing I want to talk about is a little bit more about the geometry of curvature. Now I want to recap. We have our curvature. Our curvature is k. The radius of curvature . And I think yesterday I wrote a small r. Usually for the radius of curvature we use a capital R. R is 1 over k. Some books use rho. Use rho equals 1 over k. just so you know. If the circle with radius r at a particular point, I'm going to say radius r that is tangent to a curve at a point, is called, on the concave side, is the osculating circle. Osculate means to kiss. So it's a circle that kisses the curve. And what the osculating circle does is it's very similar to what we did with a Taylor series, where we approximated a function with a constant, and then we approximate a function with a linear function, and then we can approximate a function with a second degree so the second derivatives match. So the osculating circle is an approximation of the curve where the curvature matches. So the curvature has to do with the second derivative. So it's the osculating circle near a particular point is going to be a better approximation to a curve than a linear approximation, because their first derivatives and their second derivatives agree. The center of the circle is the center of curvature. So we can, at any point on a curve, we can think about, we can approximate the point on that curve to be moving in a circle with the radius being the radius of curvature. So at any point we have this circle.
So it's like a whole bunch of assemblies, like an assembly of a whole bunch of arcs and circles, like sectors.
Right, right. So let's look at a picture of the osculating circle and talk about how we can find the center of curvature. So I'm going to put the circle, put a curve in the plane. And I'm going to draw the circle first, because it's easier for me to draw the circle and match the curve to the circle. So there's my circle. There's my center. And I'm going to say that we have this curve. And there, right there, is where those two are tangent. So there's my curve. And I'm going to draw a vector to the center of the circle of curvature. So I'm going to call that vector C. So that's a position vector for the center of the circle. And the radius of this circle is r. So the curvature, K, at that particular point is 1 over r. I'm going to draw now a position vector to the point on the curve. And I'm going to call that R. At that tangent point, what vector points to the center of the circle? The principal unit normal vector. N points to the center of the circle. So I'm going to draw in my principal unit normal vector here. So I'm going to say that's N. How could we represent, let me do that in black. How could we represent then a vector from that tangent point to the center of the circle?
Find the distance from R.
Yeah, N times R. So this vector to the center of the circle is going to be, I'm just going to add another vector here. That vector is going to be N times R. And I'm going to write it as R times N. So from the diagram, we see that C, the vector to the center of the circle, is the position vector to the point, the tangent point that we're interested in, plus R times N. This is how we can find the center this way. So this is how we'd find the center of curvature using vector methods. Position vector to the point that we're interested in. N is our principal unit normal vector at that particular point. R is the radius of curvature at that point, 1 over the curvature. And we plug those in and we get the vector that points to the center of the circle. So the osculating circle approximates the curve very closely at that particular point. There's a plane. We talked about T and N being coplanar. The plane that contains T and N is called the osculating plane. And if we take the cross product, B equals T cross N, is called the binormal vector. So T cross N, that's going to be orthogonal to the plane, to the osculating plane. The rate of change of B with respect to arc length gives you information about how the curve twists in space. So as that binormal vector changes in space, it tells you how the curve is twisting. And we use the binormal vector to define what we call the torsion of the curve. And that has to do with how it's twisting in space.
How did anyone find this out?
That's what mathematicians do. They just this is interesting. Let's do a cross product.
Look at circles all day. Do you think you would have figured this out?
You've watched Big Bang Theory, right?
Yeah.
There's one time when Leonard's talking to Penny and she says, "What did you do all day?" And he said, "I thought." That's what mathematicians, physicists do. They sit around thinking about stuff. And then every once in a while you get an idea and you write it down.
Unless there's no margins.
What's that?
Unless there's no margins.
Right. All right, I have a little demonstration with osculating circles, and then I want to talk about relate curvature back to acceleration a little bit. So let me find those demonstrations. Okay.
Are we smart enough to understand your shirt yet?
Yes, that's
Yeah.
what we learned yesterday.
Oh my god!
I couldn't see it. It's behind the monitor.
Oh my god! I mean, maybe you're not.
Oh.
What chapter are we in? We're chapter 12.
Yeah. Hard to talk. He's great.
So Beaver, you have to keep that on the recording.
It's definitely going to be on there.
See, I'm glad we're the class being preserved for the rest of the
Yeah, I'm just going to say, so just for the information of the listeners, my shirt has the formula for curvature that we derived in class yesterday. All right. So I have a lot of subscribers in like Middle Eastern countries, and so they're going to get a big kick. There was someone that got in touch with me a few years ago that was taking Calc 3 at a college and had some life situation happen. He had to move. And then where he moved to, the professor was allowing him to take his exams to get credit for Calc 3, but he wasn't attending class. So he's watching my videos for his lectures, and he'd email me questions, and he ended up getting an A in Calc 3. I thought that was pretty impressive. And he emailed me recently, relatively recently, and told me he graduated with his math degree.
Wow.
Finally. Yeah, so he got whatever situation happened, turned around, and graduated with a math degree.
Have you ever met him?
I haven't.
That man part.
We should bring him in as an inspirational speaker.
All right.
I got an A.
Something, yeah, I think I wonder if there's something's going on